Hello, my name is Anastasia Warner, and I am presenting my Honors Engineering Capstone project, Object Detection for Hardware-Accelerated Task Planning. My advisor for this project is Professor Chad Jenkins, and I worked with PhD students Anthony Opapari and Alphonsus Adu-Braden. This capstone was part of a larger robotics research project with the goal of implementing a more efficient beliefs-based planning algorithm for autonomous robotics. Our approach is to co-design a robot's planning algorithm with its hardware by parallelizing some of the processing on an FPGA. This strategy should use less time and power than current beliefs-based planning algorithms. Beliefs-based planning and probabilistic inference, for a little bit of background, are two techniques in robotic task planning, which allow for fully autonomous systems to handle uncertainty about their observations, such as the position of objects in the world. These methods help account for uncertainty and perception errors, which are common, but they require extensive computational resources and time, which can become prohibitive for robot systems that need to interact with the world and respond in real time. So we'll need to implement an algorithm on an FPGA, and then we'll need to test it. We want to conduct an experiment that requires a robot to plan actions to accomplish a goal in its environment. My capstone work was to design the perception system for this task. In the task, the digit robot will manipulate a sweeper tool to push colored blocks on a table toward a goal configuration. The task allows for some natural sources of uncertainty to arise because of the blocks being hard to detect when they're pushed together and because they're sometimes obscured by the robot arm itself. So I implemented the components necessary to detect the blocks used in the experiment, to calculate their locations, and to interface with the parallelized planning code, which uses the blocks' locations to plan the robot's movements. Designing the object detection system for this task in particular had a couple of unique challenges and constraints. First, we wanted to avoid using borders on the blocks, which are normally used in computer vision systems to make the blocks easy to detect. But we skipped this step because we wanted, like I said, a natural source of uncertainty in the system, which allows us to show off the capabilities of the beliefs-based planning methods in the algorithm. Basically, we built some error into the system on purpose to make the experiment challenging and realistic. After detecting the blocks, I needed to convert the pixel locations into a 3D location in space so that the robot can plan its movements in the real-world space. Additionally, I had to develop an easy-to-use interface between the Python detection code and the planning code, which was implemented in Julia. So, what did the detection system end up looking like? To get here, I tried a lot of iterations, using different approaches for object detection with Python's OpenCV platform, including contouring and thresholding based on difference from a base color or based on RGB values or HSV values. It turns out, actually, that segmenting the blocks is pretty easy until they're pushed together, which they will be in this experiment. This is because even high-resolution cameras can't resolve the space between the blocks very well, as you see in the top image with red-only blocks. So it took a lot of trial and error to get it right. And then trying lots of techniques with little success inspired me to finally try using blocks of different colors instead of sticking with our initial plan, which was just to use one color. I also tested the quality of 3 different cameras and chose the best one for the experiment. And I created test data sets of single color, tricolor, and multicolor block configurations, which you see depicted here, for benchmarking the perception performance. I tested the performance of 2 of my best methods, which were filtering 4 different colors in the RGB space and the HSV space, and then contouring on those colors. And you can see the results here for each of the data sets. I found that the best performance came from the RGB filtering on the multicolor data set because there were clearer borders between the blocks of different colors. I also suspect that the RGB being better might be a result of the thresholding values being a specific configuration. So when the experiment is set up, we'll need to test again to determine the best RGB and HSV settings and see which is the correct mode to use. Then here is the final design of the system. We start by getting an image from the camera stream, interfacing with ROS, which is the robot operating system. Then we filter that image by depth, do some pre-processing on it, and mask out any region that's outside the table surface. For each of the colors, we threshold the image based on the settings for that color. This returns a binary image, and we can use OpenCV to find the contours in the image. For each contour, we extract the bounding boxes, which are seen in the top image on the right in this slide. Then we can use the camera's properties and the depth data to convert the pixel locations of each box to its X and Y positions in the world and get the orientation as well. Last, the Python code will interface with the Julia code and pass along all the positions and orientations of each detected block. On the bottom right is the result of loading my detections into the planning code and displaying them in the sweeper experiment simulator. You can see in the detection result with the bounding boxes that the blocks are still sometimes hard to separate, such as in the larger green box or the orange box where the two cubes are together. This is okay because we want to give the planning algorithm some uncertainty to work around. For future directions of this work, the research team has currently completed implementing some baseline algorithms on a CPU and GPU and run preliminary tests. To complete the project, the team will implement the parallelized belief-based planning algorithm on FPGA hardware and run simulated experiments to verify its effectiveness. Then we can run the sweeper experiment in real life on the digit robot with my perception system and compare the baseline implementations to the updated accelerated approach on the FPGA. Before running the experiment, it might be necessary to tune the perception system's HSV filter settings using the final setup to get more robust thresholding. Working on this capstone project allowed me to learn about the process of completing research in the field of robotics and to take ownership of a component of an experiment. Although my work is done, there is still lots to be accomplished within the field of trying to improve belief-based planning algorithms for robotics. I'd like to thank those in the Laboratory for Progress who helped enable me to complete this capstone, especially Professor Chad Jenkins, Anthony Opapari, Alphonsus Adubredu, and Cameron Caselas. Thank you all.